It's March 8th, and the first video today is about solving recurrence relations. This is tutorial 7, question 1a. And we're asked to solve this homogeneous recurrence relation. It's a recurrence relation because you've got terms defined in terms of other terms, and it's homogeneous because that's all there is. There isn't an extra function in there anywhere that isn't an a sub something. This is the same kind of way that the first time you see this is usually in the definition of the Fibonacci sequence. And because an is defined in terms of the two previous terms, an minus 1 and an minus 2, we have to be given at least two of the values, and then for the second and up value, we calculate them from the recurrence relation. But if you think about it, if you wanted to find the a to the 100th term, you'd have to go 100 steps through the recurrence relation. So we'd like to have a closed form for this if we could, something where a to the 100 would depend just on the value 100 and some equation. And sometimes that's possible and sometimes it isn't, but linear homogeneous ones are possible, so let's step through how to do that. First we take our linear recurrence, and we stick everything on the left-hand side. You might have been able, It's going to look a little bit like a quadratic here, which isn't exactly a coincidence. By the way, you learned a longer form and a shorter form, but the longer form was really just to motivate and prove to you why the shorter form works. So we're kind of taking a shortcut here, but it's one that has been verified for you that it did work. So we're going to turn this into a quadratic, and the way I remember it is as the indices of the terms step down, the powers of your variable step up. So a to the n is going to be our constant term, a to the n minus 1 is going to be our x term, and we have to bring the minus 5 down, and then a to the n minus 2 is going to be our x squared term, and it has a coefficient of minus 6. That's all very well and good, and if you went to grade 10, which you probably did, you can factor this puppy no problem. And now the step we take kind of hinges on the fact, as you know now, the 1 over 1 minus 6x has a coefficient of 6x all to the n, and 1 over 1 plus x is just the sum of x to the n. So we're sort of using that in a sense here, because we're using the form of this, which is 6 to the n, and the form of this, which is just, well, I forgot the minus 1 because it was plus, not minus. So we can write this as a to the n being dependent on 6 to the n and minus 1 to the n. It's going to be some combination of them, and we don't know what those are, so we have to put an a and a b. And now we have two pieces of information given to us that we haven't used yet, the a0 and the a1 values. So, like Chekhov's gun, you can't, if a piece of information was given to you, the question is not done until you've used it. So we'll substitute in. We have that a0 is 1, and when we substitute, we have a to the n, which is a to the 0, is 1. And now, here's a common mistake. It's 6 to the power of n, but n is not the value, it's the subscript. So it's 0 here. So that's the same as saying that 6 to the 0 is 1, so it's just a, and negative 1 to the 0 is also 1. When we substitute a1 being 3, we have a1 out front, so that's 3. And then again, we have a6 to the exponent n, but n is 1. So it's 6 to the 1 plus b, negative 1 to the 1. Did my 1 sideways. which is the same as saying that 3 is equal to 6a minus b. So I'll, so b is 1 minus a. If we substitute that in really quick, hopefully we can get 7a is equal to 2. But I've made a mistake because that's not true. Let me skip the details and go straight to the punchline, that you will find that a is 4/7, and b, because they add up to 1, has to be 3/7. So we have our closed form now. We can write it as a to the n. Capital A is 4/7, and that was getting multiplied by 6 to the n. And b is 3/7 minus 1 to the n. And you could do 100 terms if you wanted to see if that was true or not, but it is the correct answer.